Oil shale sounds like a simple energy miracle, a rock that contains oil. But that phrase hides the most important part of the story. Oil shale is not ordinary crude oil sitting in a rock, waiting to be pumped out. It is a fine-grained sedimentary rock rich in organic material called kerogen. Kerogen is a solid mixture of organic chemical compounds, formed from ancient biological matter buried with sediment over geological time. It is related to the natural processes that create oil, but it is not yet liquid petroleum. To turn it into usable hydrocarbons, people must heat and process the rock. That makes oil shale both fascinating and difficult. The energy is there, but it is locked inside stone. The basic geology begins in ancient environments where organic matter accumulated faster than it could fully decay. Tiny organisms, algae, plant fragments, and other biological material settled into mud and sediment, often in oxygen-poor conditions. Over time, those layers were buried, compressed, and transformed into sedimentary rock. Inside some of that rock, the organic material became kerogen. Oil shales are commonly grouped by where they formed: marine deposits from ancient seas, lacustrine deposits from lake environments, and terrestrial deposits linked to land-based material. This origin matters because it affects the chemistry of the kerogen, the minerals mixed through the rock, and the practical value of the deposit. Kerogen is the reason oil shale matters, but the rock is not made of kerogen alone. It also contains inorganic minerals and vitamins, and that mixed composition affects everything about extraction. A deposit with more useful organic material may produce more liquid hydrocarbons per ton of rock. A leaner deposit may require mining, crushing, and heating huge volumes for a relatively modest yield. This is where the difference between a resource and a profitable fuel becomes clear. A rock can contain potential energy, but if too much material must be moved, heated, and cleaned up, the economics quickly become difficult. Oil shale is therefore measured not just by what it contains, but by how hard it is to unlock. One of the biggest confusions around oil shale comes from the term shale oil. In modern energy news, shale oil often refers to tight oil, actual crude oil trapped in dense shale or similar rock formations. Tight oil is produced by drilling wells, often horizontally, and using techniques such as hydraulic fracturing to let the oil flow. Famous examples include formations such as the Bakken, Eagle Ford, Niobrara, and Pierre Shale. Oil shale is different. In oil shale, the main organic material is kerogen, not free-flowing petroleum. Shale oil made from oil shale is created through heating and processing. Tight oil is already oil. Oil shale is rock that can be converted into oil. The appeal of oil shale is its scale. A 2016 estimate placed global oil shale resources at the equivalent of about 6.05 trillion barrels of oil in place. That number is enormous, and it explains why oil shale has repeatedly attracted attention during periods of energy insecurity. But oil in place is not the same as oil that can be produced cheaply, safely, or profitably. It is a geological estimate of potential content, not a promise of usable supply. Many deposits are too expensive, too water-intensive, too polluting, or too technically challenging to develop at large scale. Oil shale shows how the world can have vast underground energy resources that remain only partially usable. Oil shale can be used in two main ways. The simpler method is to burn it directly as a low-grade fuel. In that role, oil shale works more like a poor-quality solid fuel than a source of liquid oil. It can be fed into furnaces for power generation or district heating, using the organic content in the rock to produce heat. Estonia is the best-known example of a country with a long-established oil shale industry, and China also has a significant sector. Brazil, Germany, and Russia have used oil shale to some extent. But globally, direct burning remains limited because the rock is bulky, lower in energy density than many fuels, and environmentally challenging. The more ambitious use is to turn oil shale into liquid shale oil. This depends on pyrolysis, a process where the rock is heated to high temperatures with little or no oxygen. Instead of simply burning, the kerogen breaks down chemically and releases vapor. When that vapor is cooled, it condenses into liquid unconventional oil, while combustible oil shale gas can also be separated. This is the step that transforms solid organic matter into a fuel that can substitute for crude oil. But the process is not magic. The liquid product usually requires additional refining, and the heating stage consumes energy. Every ton of rock has to justify the fuel it produces. The economics of oil shale are one reason the industry has never become dominant. Conventional oil is often produced by drilling into reservoirs where pressure, permeability, and existing liquid hydrocarbons make extraction more direct. Oil shale requires more steps: mine or access the rock, crush or prepare it, heat it, collect vapors, condense liquids, manage gas, handle waste, and refine the final product. Each stage adds cost and technical risk. When oil prices are high, oil shale can look more attractive. When conventional oil is cheap or abundant, many projects become hard to justify. This boom and disappointment pattern has followed oil shale for more than a century. Land use is another major issue. Many oil shale projects involve mining large quantities of rock either from surface mines or underground operations. Surface mining can remove vegetation, reshape terrain, disrupt drainage, and leave behind pits and waste piles. Underground mining may reduce visible surface damage, but it brings its own engineering, safety, and subsidence risks. After the kerogen has been processed, the remaining spent shale still has to go somewhere. It may be chemically altered, dusty, and bulky. If not managed carefully, waste material can affect soil, air quality, and nearby waterways. The landscape cost is part of the true price of turning rock into fuel. Water can become a deciding constraint. Oil shale processing may need water for cooling, dust suppression, waste management, refining, and pollution control. Some deposits are located in regions where water is already scarce or heavily contested by cities, farms, ecosystems, and other industries. Wastewater from processing can also contain salts, organic compounds, metals, or other contaminants that require treatment. This means oil shale is not only an energy question, it is also a water management question. A project that looks technically possible on paper may face serious limits if it competes with local water needs or creates wastewater problems that are expensive to solve. Air pollution and greenhouse gas emissions add another layer of difficulty. If oil shale is burned directly, it releases carbon dioxide and air pollutants like other fossil fuels, often with extra complications because of the mineral content of the rock. If it is processed into shale oil, emissions occur during mining, transport, heating, refining, and finally when the fuel is burned. The pyrolysis stage can be energy-intensive, which may raise the carbon footprint before the oil even reaches a vehicle or industrial user. Modern pollution controls can reduce some impacts, but they cost money and do not remove the basic challenge. Oil shale is a carbon-heavy route to liquid fuel. So oil shale is best understood as a resource of enormous potential and stubborn limitations. It contains kerogen that can become liquid hydrocarbons, and global deposits are vast. It can provide heat, power, chemical feedstocks, and unconventional oil. Yet the same process that makes it useful also makes it difficult. The rock must be mined or heated, the organic material chemically transformed, the product refined, and the waste managed. Estonia and China prove that oil shale industries can exist, but the limited global adoption shows why it has not replaced conventional oil. Oil shale is not a hidden shortcut to endless energy. It is energy locked behind geology, engineering, economics, and environmental cost. If you found this helpful, please like this video and subscribe for more explainers.